They say the best magic tricks are the ones where you see the secret and still can't believe it happened. On a spring day in 2001, Boeing walked onto a stage and performed exactly that kind of illusion in front of the entire aviation industry. They unveiled an aircraft so radical, so technically ambitious, so utterly unlike anything they had ever built that it made Airbus's engineers physically uncomfortable. The Sonic Cruiser promised to fly passengers at nearly the speed of sound, to slice hours off intercontinental journeys, to fundamentally rewrite what commercial flight could be. It looked like a weapon pretending to be transportation, all sharp angles and predatory intent, canards jutting forward like the aircraft was perpetually leaning into a fight it was eager to start. Airbus had just bet their company, their reputation, and nearly a decade of development time on building the largest passenger aircraft in history. And now their biggest rival was holding up, something that made that bet look slow, obsolete, and tragically misguided before a single A380 had carried its first paying customer. Here's what makes this story extraordinary. Boeing never intended to build it. Not really, not ever. The Sonic Cruiser was a feint, a calculated misdirection so audacious that even after it worked, even after Boeing canceled the program and pivoted to something completely different, people still argue about whether it was genius or accident. That phantom aircraft, the one that never burned a gallon of fuel at altitude, never carried a single passenger, never had a rivet driven into a fuselage that didn't exist. That aircraft changed everything about how we fly today. It bankrupted the business case for the most ambitious passenger jet ever conceived, triggered a materials revolution that nearly destroyed Boeing itself, shifted hundreds of billions in airline capital toward a future that would never arrive, and smuggled technologies into commercial aviation that are now so standard, we forget they were once considered impossible. The Sonic Cruiser never flew, but it won a war that most people didn't realize was being fought. This is the story of aviation's greatest bluff, and how an aircraft that existed only as images and promises rewrote the rules of an entire industry while everyone was looking directly at it. What happened next would reshape the entire architecture of global aviation, trigger the collapse of the hub and spoke model that had dominated for decades, prove that sometimes the most powerful move in business is to bet everything on something you never intend to build, and demonstrate that in aviation, the futures you force your competitors to commit to matter far more than the metal you actually manufacture. Boeing showed the world an impossible dream. Airbus chased it. And while they were running in the wrong direction, Boeing quietly built the future that actually mattered. The late 1990s were deceptive years for commercial aviation. Traffic was growing predictably, profits were reasonably healthy, and the industry seemed to have settled into comfortable assumptions about its future shape. Boeing and Airbus had carved up the market into complementary niches. Boeing dominated the middle market with the 737 and owned long-haul efficiency with the 777. Airbus had climbed from nowhere to challenge Boeing across the narrow-body spectrum and was making serious inroads with the A330. Both companies looked at growth projections and saw runway congestion, slot constraints at major hubs, and air traffic control systems straining under increasing complexity. The question wasn't whether demand would grow, it was how the system would accommodate that growth without collapsing under its own weight. Airbus saw this bottleneck and made what seemed like an ironclad logical deduction. Airports were not getting meaningfully larger. Building new runways required political will that evaporated whenever property values and noise concerns entered the conversation. The number of viable slots at major hubs was functionally frozen. Therefore, the only path to growth was vertical. Pack more people onto each airplane, maximize revenue per slot, and turn major hubs into fortress operations where your largest aircraft became the only rational choice. The A380 emerged from this analysis as something close to destiny, a 550-seat colossus that would make hub-and-spoke economics so compelling that airlines would have no choice but to restructure their networks around it. Airbus began pouring resources into the program, courting launch customers, and building political support across European governments who saw the project as essential to maintaining the continent's position in aerospace. By 2000, the A380 had moved past the point of return. It was real, funded, and inevitable. Boeing strategists looked at the exact same data and reached a conclusion that would have seemed heretical just a few years earlier. They believed the hub-and-spoke model was not the future, but a temporary adaptation to limited range and efficiency. Passengers routed through congested hubs were not grateful for the experience. They were trapped by it. Business travelers paying premium fares were increasingly hostile to connections that added hours to journeys and multiplied failure points. Hidden demand existed everywhere for direct service between city pairs that didn't justify 400-seat aircraft, but could easily fill something smaller, more efficient, and more frequent. The future, Boeing concluded, was not bigger hubs. It was the elimination of hubs altogether. Point-to-point flying would unbottle the system, reduce travel time, improve passenger satisfaction, and allow airlines to capture revenue they were currently bleeding to inconvenience. But here's where the logic encountered physics. Point-to-point only works economically if you change the fundamental value equation. You can't just fly the same airplane on thinner routes and hope for profit. You either need to cut costs so drastically that marginal routes become viable, or you need to create new value that passengers will pay for. In 2000, incremental efficiency gains couldn't deliver the cost revolution required. Engines were improving by single-digit percentages per generation. Aerodynamics had been refined for decades. Aluminum airframes were already highly optimized. Evolutionary improvement wasn't enough. Boeing needed something discontinuous, something emotionally powerful enough to shift passenger behavior and commercially compelling enough to justify premium pricing. They needed speed. Time is the one resource you can't manufacture more of, and every frequent flyer knows its value intimately. Cut 2 hours from a transatlantic flight, and you're not just saving time, you're reclaiming an evening with family, arriving fresh for a morning meeting, or making a same-day round trip possible where it wasn't before. Speed doesn't just compress schedules. It fundamentally changes what's accessible, what's worth attempting, what business models become viable. Boeing calculated that cruising at Mach 0.98, just shy of the sound barrier, could reduce flight times by roughly 15 to 20% compared to conventional jets. That translated to real, tangible value worth real, tangible money. The Sonic Cruiser was designed to capture that value and convert it into a sustainable business advantage. Flying that close to Mach 1 without crossing it is one of the most demanding challenges in aerodynamics, a high-wire act where margins evaporate and physics stops forgiving mistakes. As aircraft approach the speed of sound, airflow over curved surfaces accelerates unevenly. Some regions go supersonic, while the free stream flow remains subsonic, creating a chaotic mixed regime where shock waves form, collapse, and reform across wings and fuselage. These shock waves are energy thieves. They dramatically increase drag, create buffeting that can damage structure, and trigger flow separation that destroys lift. Conventional airliners are designed to cruise comfortably below this transonic nightmare, typically around Mach 0.84 to 0.86, where the penalties are manageable and predictable. Boeing chose to charge directly into the turbulence. The solution was area rule, a principle discovered in the 1950s that revolutionized supersonic fighter design but had never been fully exploited in commercial transport. Area rule dictates that an aircraft's drag near Mach 1 is determined primarily by how its total cross-sectional area changes from nose to tail. Smooth, gradual changes minimize shockwave strength. Abrupt changes, like where a wing joins a fuselage, create violent flow disruptions. The Sonic Cruiser's entire shape was sculpted around this principle. The fuselage pinched inward where the wings attached, creating a wasp-waisted profile that looked alien, compared to traditional tube and wing designs. The wings themselves were highly swept, almost delta-like in plan form, blending smoothly into the body rather than bolting on as separate structures. Forward canards, small winglets ahead of the main wing, provided pitch control and managed airflow in ways that reduced overall drag and improved stability at high speed. The resulting form looked less like an evolution of existing airliners and more like a dart, every surface purpose-built to cheat physics just enough to make the impossible merely difficult. Engines were equally problematic. Turbofans designed for high subsonic cruise operate most efficiently at lower speeds, where their large bypass ratios create thrust without excessive fuel burn. Push them toward Mach 1 and everything gets harder. Inlet shocks form. Compressor stages struggle. Temperatures spike. Fuel consumption explodes. Boeing explored modified high bypass designs that could tolerate higher cruise speeds without destroying their economics. But the margins were brutal. Every fraction of a Mach number demanded compromises in durability, maintenance intervals, and noise signatures. The faster you fly, the more fragile everything becomes, and the more expensive failure gets. Weight became the other unforgiving constraint. At high subsonic speeds, aerodynamic forces scale aggressively. Structures must be stronger, which traditionally means heavier, which requires more thrust, which burns more fuel, which requires more fuel capacity, which adds more weight in a vicious spiral that quickly makes the entire concept unviable. Aluminum, aviation's structural backbone for nearly a century, simply couldn't deliver the strength-to-weight ratios the Sonic Cruiser demanded. Steel was worse. Titanium was exotic and expensive. The only path forward was composites, specifically carbon fiber reinforced polymers that offered extraordinary stiffness and fatigue resistance at densities that made aluminum look like lead. This is the moment where the story shifts from speed to materials, from public spectacle to quiet revolution. Boeing didn't experiment with composites on the Sonic Cruiser. They committed to them as the foundational technology that would make or break the program. This wasn't a few panels or secondary structures. This was primary load-bearing fuselage sections, wing structures, and control surfaces, all constructed from materials that commercial aviation had barely tested at scale. The learning curve was vertical. Composites don't bend and crack like metal. They delaminate, a failure mode that's invisible until it's catastrophic. They don't conduct electricity, turning lightning strikes from a solved problem into an active threat. They require autoclaves the size of small buildings, curing processes that take hours instead of minutes, and quality control techniques that didn't exist yet. Boeing was effectively proposing to reinvent how large aircraft were manufactured while simultaneously pushing aerodynamics into uncharted territory. Lightning protection became particularly critical and would echo through aviation for decades afterward. Aluminum fuselages are naturally conductive. Lightning strikes dissipate harmlessly across the metal skin and exit through controlled discharge points. Carbon fiber is an insulator. Without protection, a lightning strike could punch through composite structure, ignite fuel vapors, or destroy flight control systems. Boeing's solution involved embedding fine conductive meshes into the composite layup, creating an artificial conductive path that could safely channel electrical currents. It worked, but it added weight, complexity, and cost. More importantly, it introduced a new failure mode that wouldn't fully surface until years later, when moisture ingress, impact damage, and aging mechanisms began degrading those protective layers in ways nobody had predicted. Qatar Airways would eventually ground its entire A350 fleet over surface degradation, concerns linked directly to composite lightning protection, triggering a legal war with Airbus that dragged through courts until a settlement finally closed the matter in 2023. The roots of that billion-dollar dispute trace directly back to the composite revolution the Sonic Cruiser accelerated. When Boeing revealed the Sonic Cruiser concept in March 2001, industry reaction split sharply. Airlines were intrigued. Some, particularly those serving long, thin routes, were genuinely excited by the possibility of offering differentiated service that could command premium fares. Others were skeptical, questioning whether passengers would actually pay meaningfully more for speed, whether fuel costs would destroy the economics, and whether Boeing could actually deliver on the promised performance. Airbus publicly dismissed the concept as a distraction, insisting that capacity, not speed, was where the market was headed. Privately, there was concern. If Boeing was serious, if they actually pulled this off, it would make the A380 look slow, inefficient, and dated before it entered service. Then the world exploded. September 11, 2001 didn't just devastate passenger demand. It fundamentally reset the industry's risk calculus and time horizon. Airlines that had been cautiously optimistic about the future were suddenly fighting for survival. Capital markets froze. Financing for new aircraft evaporated. Long-term strategic bets were shelved in favor of immediate cost reduction. At the same time, oil prices, which had been relatively stable through the 90s, began a sustained climb that would dominate airline economics for the next 2 decades, spiking above $140 per barrel by 2008. And remaining structurally higher than historical norms even during downturns. An aircraft optimized for speed at the expense of fuel efficiency suddenly looked like a liability, a luxury the industry could no longer afford. Boeing recognized this faster than most anticipated. Engineers working on the Sonic Cruiser had already refined many of the technologies that would be needed regardless of the final speed. Composite manufacturing processes had been developed. Suppliers had been qualified. Aerodynamic tools had been validated. Electric system architectures had been designed. All of this work could be redirected toward a different design optimized for efficiency rather than speed, while still delivering the point-to-point capability Boeing believed would define the future. In December 2002, Boeing officially canceled the Sonic Cruiser and simultaneously announced the 7E7 program, which would become the 787 Dreamliner. The new aircraft would cruise at conventional speeds, around Mach 0.85, but would fly farther than anything in its class, burn 20% less fuel than existing aircraft, and enable economically viable point-to-point service on routes that had never been possible before. Critically, it would inherit the Sonic Cruiser's composite construction almost wholesale, betting that the weight savings alone would deliver revolutionary efficiency. The 787 would be the first commercial airliner with a composite fuselage and wing, a gamble so large it would take Boeing to the edge of bankruptcy when manufacturing problems compounded years later. Airbus had no such flexibility. The A380 was politically locked in, contractually committed, and too far along to abandon without catastrophic financial and reputational consequences. European governments had guaranteed loans. Airlines had placed deposits. Suppliers had retooled factories. The program was too big to fail, which meant it had to succeed even as the market it was designed for began to dissolve. By the time the A380 entered service in 2007, twin-engine long-haul jets like the 777 and later the 787 and A350 were already proving that hub-and-spoke economics could be bypassed entirely. Airlines discovered they could serve the same passenger volume more profitably with higher frequencies on smaller, more efficient aircraft. The A380 became an icon, beloved by passengers for its space and quietness, but economically fragile. Emirates became its lifeline, ordering enough aircraft to keep production viable, but even that support eventually ran out. Airbus delivered the last A380 in December 2021, just 251 aircraft across 14 years, a fraction of the thousands that original business cases had projected. The Dreamliner's path was anything but smooth. Composite manufacturing at scale proved far harder than anticipated. Boeing's aggressive outsourcing strategy created coordination nightmares. Traveled work, where components arrived incomplete and required extensive rework, ballooned. The program was years late and billions over budget. When the aircraft finally entered service in 2011, lithium-ion battery fires grounded the entire fleet just months later, triggering investigations that exposed gaps in certification processes and raised uncomfortable questions about regulatory oversight. Manufacturing defects, particularly with fuselage joints and debris left inside structures, led to repeated production pauses through the late 2010s and into the 20s. Boeing's reputation took damage that compounded when the 737 MAX disasters exposed deeper cultural and safety problems within the company. Quality issues persisted into 2024, with door plug failures on 737s and ongoing scrutiny of production standards forcing leadership changes and comprehensive operational reviews. Yet, despite everything, despite the delays and the defects and the reputational damage, the fundamental bet held. Composite wide-bodies became the industry standard. Airbus launched the A350 as a direct response, using similar composite construction to compete on efficiency and range. Range increased dramatically. The 787-900 could fly nearly 8,000 nautical miles, opening direct routes like Perth to London that had been impossible before. Fuel burn dropped significantly. Point-to-point flying reshaped global networks exactly as Boeing had predicted, with smaller aircraft serving thinner routes more frequently and profitably than hub concentration ever could. Seen through this lens, the Sonic Cruiser accomplished exactly what it was designed to do, despite never turning a single wheel. It was leverage, pure and calculated. It forced Airbus into a maximalist commitment to hub-and-spoke economics, at precisely the moment that model was beginning to fracture. It gave Boeing political cover and engineering justification to spend billions developing composite manufacturing at a scale nobody had attempted. It reframed industry conversation around what passengers actually valued, not what manufacturers found convenient to build. It was a beautifully engineered decoy that carried real science inside a fictional future, and when the moment was right, Boeing stripped away the fiction and kept the science. Today, as startups like Boeing Supersonic chase quieter, more sustainable supersonic flight, and established players explore hydrogen propulsion and radical efficiency improvements, the questions Boeing wrestled with 2 decades ago are back in circulation. Speed versus efficiency, materials versus maintainability, vision versus timing. How much will passengers pay for saved time? What regulations will governments impose? Which technologies are ready and which are still too fragile? The Sonic Cruiser sits at the center of that history, the most elegant aircraft never to leave the ground. A reminder that in aviation, progress is not always measured in flights logged or passengers carried. Sometimes it is measured in the futures you force competitors to commit to, the technologies you prove are viable when nobody is watching, and the one move you make while everyone is staring somewhere else. Boeing showed the world an impossible dream, and while Airbus chased it, they quietly built the future that actually mattered. That's not just clever, that's masterful.